Hello, today we're going to explore a powerful technique in calculus called implicit differentiation. By the end of this video, you will be able to understand what implicit differentiation is, why it's necessary, and how to apply it to find the derivative of complex equations. You're already familiar with differentiating functions, where y is explicitly defined in terms of x, like y equals x squared. In this case, we can easily find the derivative, dy by dx, which is 2x. This is called explicit differentiation because y is explicitly given as a function of x. But what if the equation isn't solved for y? What if y is mixed in with x, like in the equation x squared plus y squared equals 25? This equation represents a circle. Here, y is not explicitly defined as a function of x. We could try to solve for y, but we'd get y equals plus or minus the square root of 25 minus x squared, which is two separate functions. This is where implicit differentiation comes in. It's a method that allows us to find the derivative, dy store dx, without first solving for y. We use it when an equation defines a relationship between x and y, but it's difficult or impossible to isolate y. The key idea is to treat y as an unknown function of x, and then differentiate both sides of the equation with respect to x. The most important rule to remember is the chain rule. When we differentiate a term involving y, we must multiply by dy by dy dx. For example, the derivative of y squared with respect to x is 2y times dy by dx. We differentiate y squared as if it were x squared, getting 2y, and then we multiply by the derivative of the inside function, which is y, giving us dy by dx. So to recap, implicit differentiation is a technique for finding the derivative dy dx when y is not explicitly defined as a function of x. We do this by differentiating both sides of the equation with respect to x, remembering to use the chain rule on any term involving y. Let's walk through the general process for implicit differentiation. This will give us a clear roadmap for solving any problem. First, we'll look at the step-by-step process, and then we'll apply it to our first example. Step 1 is to differentiate both sides of the equation with respect to x. Remember, this is the crucial first step. Step 2 is to apply the chain rule. For any term that contains y, you'll differentiate it as usual, but then you must multiply the result by dy dx. This is the most common place for errors, so be careful. Step 3 is to gather all the terms that contain dy/d x on one side of the equation. It's often easiest to move them to the left side. Step 4 is to factor out dy dx from the terms you've collected. This will leave you with dy dx times some expression. And finally, step 5 is to solve for dy dx by dividing both sides of the equation by the expression you factored out. This gives you the final derivative. Let's apply this process to our first example, the circle equation. We want to find dy by dx for the equation x squared plus y squared equals 25. Step 1. Differentiate both sides with respect to x. The derivative of x squared is 2x. The derivative of y squared is 2y times dy by dx. And the derivative of the constant 25 is 0. Step 2 was to apply the chain rule, which we just did for the y squared term. Step 3. Gather terms with dy's by dx. We only have one, so we'll move the 2x to the other side by subtracting it. Step 4. Factor out dy dx. It's already factored. Step 5. Solve for dy dx by dividing by 2y. The 2's cancel, leaving us with dy dx equals negative x over y. And there you have it. We found the derivative without ever solving for y. This derivative tells us the slope of the tangent line to the circle at any point x, y on the circle. Now let's tackle a more complex example that requires the product rule. Our goal is to find dy by dx for the equation x times y plus y squared equals 2x. Notice the first term, x times y. This is a product of two functions of x itself, and y, which we are treating as a function of x. This means we must use the product rule. Recall the product rule. The derivative of u times v is u prime v plus uv prime. In our case, let u equal x and v equal y. The derivative of u prime, is the derivative of x, which is 1. The derivative of v prime, is the derivative of y, which is dy by dx. So the derivative of xy is 1 times y plus x times dy by dx. Now we can differentiate the entire equation. Differentiating both sides with respect to x, we get the derivative of xy, which is y plus x dy by dx, plus the derivative of y squared, which is 2y dy by dx, equals the derivative of 2x, which is 2. Next, we gather all the terms with dy dx on one side. We'll move the y term to the right side by subtracting it. Now we factor out dy by dx from the left side. This gives us dy by dx times the quantity x plus 2y. Finally, we solve for dy by dx by dividing both sides by x plus 2y. Our final answer is dy by dx equals the quantity 2 minus y divided by the quantity x plus 2y. This example shows how implicit differentiation can be combined with other differentiation rules, like the product rule, to handle more complicated equations. For our third example, let's see how to handle a quotient. We want to find dy by dx for the equation y equals x squared over y plus 1. This equation is already solved for y, but the right side contains y. We could use the quotient rule, but it's often easier to first rearrange the equation to eliminate the fraction. Let's multiply both sides by y plus 1. This gives us y times the quantity y plus 1 equals x squared. Expanding the left side, we get y squared plus y equals x squared. Now we have an equation without a fraction, which is much simpler to differentiate implicitly. Let's differentiate both sides with respect to x. The derivative of y squared is 2y dy by dx. The derivative of y is dy by dx. And the derivative of x squared is 2x. Next, we factor out dy by dx from the left side. This gives us dy by dx times the quantity 2y plus 1. Finally, we solve for dy by dx by dividing both sides by 2y plus 1. The result is dy by dx equals 2x divided by the quantity 2y plus 1. This example demonstrates a useful strategy. Sometimes a little algebraic manipulation at the beginning can make the implicit differentiation process much smoother. Let's recap what we've learned today. We started by understanding that implicit differentiation is a technique for finding the derivative dy by dx when y is not explicitly defined as a function of x. The key rule is the chain rule. Whenever you differentiate a term involving y, you must multiply by dy dx. We then outlined a 5-step process. Differentiate both sides, apply the chain rule, gather terms with dy dx, factor it out, and finally, solve for dy dx. We worked through 3 examples, showing how to apply this process to a basic implicit equation, one requiring the product rule, and one that was simplified by algebraic manipulation. Now, it's your turn to practice. Here are a few problems for you to try. Pause the video here and work through these problems on your own. When you're ready, unpause to see the detailed solutions. Welcome back. Let's go through the solutions to the practice problems. First, let's solve for dy by dx in the equation x cubed plus y cubed equals 6xy. Differentiating both sides, we get 3x squared plus 3y squared dy by dx on the left. On the right, we use the product rule on 6xy, which gives us 6y plus 6x dy by dx. Gathering the dy by dx terms on the left and the other terms on the right, we get 3y squared dy by dx minus 6x dy by dx equals 6y minus 3x squared. Factoring out dy by dx, we have dy by dx times the quantity 3y squared minus 6x equals 6y minus 3x squared. Finally, dividing to solve for dy by dx, we get 6y minus 3x squared, all over 3y squared minus 6x. We can simplify this by dividing the numerator and denominator by 3, giving us 2y minus x squared, all over y squared minus 2x. Let's move on to the second practice problem. We need to find dy by dx for the equation sine of y equals x squared plus y. Differentiating both sides, the derivative of sine of y is cosine of y times dy by dx. The derivative of x squared is 2x. and the derivative of y is dy by dx. Now, we gather the dy dx terms on the left side. We subtract dy dx from both sides. Factoring out dy by dx, we get dy by dx times the quantity cosine of y minus 1 equals 2x. Solving for dy by dx, we divide by cosine of y minus 1. The final answer is dy by dx equals 2x divided by the quantity cosine of y minus 1. And finally, let's look at the solution to the third practice problem. We need to find dy by dx for the equation x squared over y plus y squared over x equals 2. This problem involves quotients. We could use the quotient rule twice, but a simpler approach is to first clear the denominators by multiplying the entire equation by the least common denominator, which is xy. Multiplying every term by xy, we get x cubed plus y cubed equals 2xy. Notice that this is the same equation as our first practice problem, just with a 2 instead of a 6 on the right side. We can follow the same steps. Differentiating both sides, we get 3x squared plus 3y squared. Dy by dx equals 2y plus 2x dy by dx. Gathering the dy by dx terms on the left, we have 3y squared dy by dx minus 2x dy by dx equals 2y minus 3x squared. Factoring out dy by dx, we get dy by dx times the quantity 3y squared minus 2x equals 2y minus 3x squared. Finally, solving for dy by dx, we get 2y minus 3x squared all over 3y squared minus 2x. Great job working through those problems. You've now seen how to apply implicit differentiation in a variety of situations. Let's conclude with a final thought on why implicit differentiation is so important. It allows us to find the derivative of a relationship between x and y, even when that relationship isn't a function. For example, a circle is not a function because it fails the vertical line test. But with implicit differentiation, we can still find the slope of the tangent line at any point on the circle. This technique is also a fundamental tool for solving related rates problems, where you're given the rate of change of one variable and need to find the rate of change of another related variable. You are now equipped to understand and apply implicit differentiation. Keep practicing, and you'll master this essential calculus skill. Thank you for watching.